My three sections all ended up in different spots where they stopped, so the thing that made the most sense was just start at the beginning of this example and just run through everything from there. So the first one, which is one where we do have a large enough sample size where we don't need the normal probability plots. I think we said that in every section. If we needed them, they'd be there, and they're not there. But the other piece that we need is that it is a random sample, which is right there. And then the sample size is essentially right next to it. So 35 is bigger than 30. So is it random? Well, we do have a random sample. So that's taken care of. And then for the large enough n or nearly normal population, that's really a one or the other type of situation where if you have a large enough n, you can just say you have a large enough n and you can apply the central limit theorem and you don't have to worry about it. And that's where we are here. If n was smaller, which will happen in the other examples, then you have to check the normal probability plot, you have to check the box plot. But here we do not have to do that because n is 35. So that means that n is greater than or equal to 30. So it is large enough to apply the central limit theorem. So large enough to apply CLT. One thing that is worth mentioning with this problem is there's a different alpha. Alpha's 0.01 here. So one reason why you might change your alpha is because of the two ways that you could be wrong with the decision that you make. Because you could make the correct decision at the end of the test, but you could be wrong. And the ways you could be wrong is either the null is true, but you reject it, or the null is false and you don't. That's a thing that's in section 9.4 in more detail. But the main reason you change your alpha is if one of those errors is a lot worse than the other. And considering what the context is here, the thing that would be really bad would be if the well was not safe and it was considered to be safe. So since we're looking for evidence that the well is safe, that the mean level of arsenic is less than 8 parts per billion, we're making it really tough to make the mistake or make the error of if it's unsafe to conclude that it is by pushing the alpha down lower. So that's why it's 0.01 instead of 0.05. It's because of that. It's because one way of being wrong in this case is a lot worse than the other just because of the context. So you kind of adjust for that. But as far as the hypotheses go, the thing that we're looking for is evidence that the well is safe, which is that the mean level of arsenic is less than 8 parts per billion. So that less than 8, there's your alternative hypothesis right there. So this one is for a mean, so mu less than 8. And then that means that the null is mu equals 8. And so there are our hypotheses. In the next step, what we know about the sampling distribution under the assumption that the null is true. Well, the first thing is that we can't apply the central limit theorem. We have a big enough n for that. So we do expect it to have an approximately normal shape. However, we're going to use the t-distribution to get the p-value because we don't have sigma. So down here where the standard error is, how we've got an s on top instead of a sigma on top. Because of that, that's why with means you use the t-distribution. So that's what we're going to do. So the degrees of freedom is n minus 1 and n's 35. We should have 34 degrees of freedom like we do right here. And then the mean, the mu 0, that's the part that comes from the null. Right? That's the part that comes from assuming that the null is true. So if the null is that mu equals 8, if we're assuming that's true, that's what we're going to have for the mean of the sampling distribution. And we should be able to get the test statistic and p-value from here. Computing the test statistic, we end up with negative 2.491. So then I made the drawing of it over here. So this is supposed to be a t-distribution with 34 degrees of freedom. And t-distribution by definition always centered at 0. So we know it's a left tail because we had the less than in the alternative hypothesis. So the test statistic is our cutoff, and then it's just going to be this little left tail over here. I don't expect the p-value to be very big. And we would use t-CDF in order to get it, because we're using a t-distribution this time. And this is what we end up with for the p-value. So the probability of getting an x bar less than or equal to 7.2, after we do the standardization, it's the same thing as the probability of getting a test statistic less than or equal to negative 2.491. So since this is a test for a mean, use t-CDF, not normal CDF, and it's going to be a left tail bounded by the negative 2.491, so that's the upper bound. No lower bound, so we need the negative 1e99, and then 34 for the degrees of freedom. And you do get a little tiny p-value here. You get 0.0089. So the decision, even though we cut the alpha way down, we still got a p-value that was smaller. So we are going to reject the null. So the p-value is less than alpha. Even if we have a different alpha, this still works the same way. If the p-value is less than alpha, you're going to reject the null. Otherwise, you're not going to reject the null. So here, we are going to reject the null. And that would mean that there is sufficient evidence to conclude what's in the alternative for the conclusion. And what the alternative was that the well was safe. So the mean level of arsenic in that well is less than 8 parts per billion. The second example has a small sample size, and that's why the graphs are showing up. So if you look up here, we have random sample of 20 current FICO scores. So 20 is not that big, it's less than 30, and since it's less than 30, we can't just immediately jump to the central limit theorem. We've got to make sure that things look okay here. So for the large enough or nearly normal condition for inference, we got to go the nearly normal way this time because we don't have large enough, right? 20 is too small. So the normal probability plot is supposed to look relatively straight. It looks that way. It's not perfect, but it doesn't look too far off. And then the box plot doesn't have any outliers. So we are getting the things that we're supposed to see, but we do have to check them here because the sample size is small. So there's our n. I guess I can start labeling this stuff. We're going to need to know that we have a random sample when we get to the assumptions for inference, so we're going to get there pretty quickly. And then, let's see, other things in the wording. So we have the average FICO credit score from last year, that's 714. And then that sentence underneath the sample data, does the sample provide evidence that the average FICO credit score is no longer 714? So this right here tells you what we're looking for evidence of, so that's going to be our alternative hypothesis, and no longer could go either way, right? No longer could be higher than 714, no longer could be lower than 714, so that means that we have to consider both directions, and that no longer means that we would have a not equal to in the alternative hypothesis. So we're going to be doing a two-sided or two-tailed test here. Additionally, I wrote in the sample mean and sample standard deviation up here. I know they're visible kind of if you look down here. They're next to the normal probability plot, but those numbers look kind of tiny, and I figured once this video is actually converted, it ends up being smaller, and I wasn't sure if those would be readable. So that's what they are, the 701.3 and the 79.1. We're certainly going to need them when we have to compute the test statistic. Since all of these parts have kind of been mentioned, I figured it made sense to go ahead and fill them all in. So it does say random sample, right? That's in the wording, random sample of 20 current FICO scores, so that takes care of the randomization. And then with the graphs, it's not perfect, but it's relatively straight in the normal probability plot, and that's what we want to see. No outliers in the box plot, and those two together are enough to say it looks like we have a nearly normal population, which means that we can go forward. Then the other thing that we had said was that there is a two-sided alternative. There's a not equal to in the alternative hypothesis because of the no longer 714. So that's essentially going to be your alternative. Mu is not equal to 714, which means the null is that mu is equal to 714. Things that we know about the sampling distribution of x bar, assuming the null is true, we do get the approximately normal shape. It's not because of the central limit theorem this time, because n was not big enough for that, but we checked the graphs, we said it looks like we have a nearly normal population, and if you have a nearly normal population, you'll get a nearly normal sampling distribution too. And we are going to use the t-distribution to get the p-value because this involves a mean, and that's the distribution we use with means. Then the mean of the sampling distribution would be mu, but if we're assuming the null is true, that's 714. And then the standard error, we have s from up above, that's 79.1. Divide that by the square root of 20, and there's the standard error. We have all the pieces to compute the test statistic because we have the sample measures, we have our null value, we have the sample size. So if you sub everything in and simplify, you get negative 0.718, at least to 3 places. And we're going to use a t-distribution with 19 degrees of freedom to get the p-value. And we've got a two-sided alternative, so we do have the left tail bounded by the negative 0.718, but we also have to have a right tail of the same size bounded by positive 0.718. So we should get a pretty big p-value here. And we do get a pretty big p-value here. So first I just wrote it as left tail plus right tail. And then in order to save a little bit of work, you can just double one of the tails since they are the same size. I doubled the one that has the real test statistic in it, so the left tail, but you could double the other one and you'll get the same thing. So if you use TCDF, compute the area in that left tail or the probability in the left tail and then multiply by 2, you get a pretty big p-value this time. You get 4815. So I don't think we're going to reject the null here. With a gigantic p-value like that, of course it's going to be way above alpha. So we are not going to be rejecting the null, and that would mean that in the full formal conclusion, we don't have enough evidence, or we have insufficient evidence to conclude what's in the alternative. So insufficient evidence to conclude that the average FICO credit score is no longer 714. This third example is a little bit different. Not because of the small sample size, we already played that game in the last one, but it's a little bit different because some of the work is already done. If you scroll through this one, you can see it, that there's output there from Minitab, and that does shorten this one up a little bit. So let's see what we got here. So hemoglobin count in grams per 100 milliliters of whole blood has a distribution that's approximately normal, with population mean of approximately 14 for healthy adult women. Okay, so the approximately normal population, we could kind of just hand wave it from there, but I figured stick to how we usually do it. If we have small samples, get those graphs in there. So, alright, suppose that a female patient has taken 12 laboratory blood tests during the past year, and we're going to treat those like a random sample. So we have a sample size of 12, not very big, not big enough for the central limit there. Then what we're looking for, does this information indicate that the population mean hemoglobin count for this patient is higher than 14? So we're looking for evidence of this right here, and that would imply that it looks like we're going to have a one-sided alternative, specifically one with a greater than in it. And then we're going to use alpha 0.01 again. For the assumptions or conditions for inference, it did say to regard those measurements as a random sample, so that should take care of the randomization. And then it also said that you could expect the population to be normal, but I figured stick with the graphs, that is typically what you have to do. So when you look at the normal probability plot, again, not a perfect straight line, but that's okay. It's still the general overall pattern through there. So roughly straight, and then I don't see any outliers here in the box plot, so we're good to go there. So we can say, all right, it does look like we have a nearly normal population. Then with the hypotheses, we said there's going to be a greater than in the alternative because it said higher than 14. So higher would translate to greater than, and those are what our hypotheses should look like. For this example, just to do something a little bit different, I have it based on what you'd get as Minitab output rather than going through the computation of the test statistic and then getting the p-value with the calculator. So if you look up toward the top, that's where the sample data shows up. So where it says mean and standard deviation, those are the mean and standard deviation from the sample. So X bar and S, and then SE mean, SE stands for standard error. So that's S over the square root of n, right? We said that that's what the standard error is, right? It's like the standard deviation of the sampling distribution, but with S instead of sigma. So yeah, that's what that would be. It's S over the square root of n. If you take 2.708 and divide by the square root of 12, you should get 0.782. Then down toward the bottom, so the tests are right there, or the hypotheses are right there, and they're what we said they were supposed to be. And then the thing that's called the t-value is the test statistic. And then the p-value is what you'd expect. That is just the p-value. Minitab rounds to 3 places with that, rather than, if it's really small, putting it into scientific notation. So it's not really 0, it's just that to 3 places it would round down to 0. If the p-value rounds down to 0, it's going to be less than alpha, no matter what alpha is, really. And so here, even though we have a small alpha, the p-value is still going to be smaller than that. So as usual, the p-value is less than alpha. We're going to reject the null. And that means that for the full conclusion, we have enough evidence or sufficient evidence from our sample to conclude that the alternative looks like it's true. So here that's that the mean hemoglobin count for this patient is greater than 14. So greater than 14 grams per 100 milliliters of whole blood. This is the beginning of the third part of the Chapter 9 notes, but this part here is still Section 9.3 with how to do a hypothesis test using a confidence interval. Basically, the way that it works is it's got to be a two-sided test, since a confidence interval is a two-sided concept as well, so it's got to match up. So it has to be a two-sided test, and then essentially what you do, and you can kind of see it down here, I think a little easier, is that you have to match up alpha with the confidence level. So you want, if they're in proportion form, you would want them to both add up to 1. If they're in percent form, you want them to add up to 100. So if alpha is 0.05, it says use 95% confidence. That's because 0.05 plus 0.95 is 1, or 5 plus 95 is 100. Same thing with if alpha is 0.1, you're going to use 90% confidence because those are going to add up correctly. If alpha is 0.01, use 99% confidence because 0.01 plus 0.99 is going to be 1, right? So you have to have the confidence level and the alpha, your significance level. You got to get them to match up. And then the way that it works is you use the idea that the confidence interval is supposed to give you a range of plausible values. So that's kind of in this third bullet point up here. So if the value that's in the null is inside the confidence interval, then it would be considered to be a plausible value. And if it's a plausible value, you wouldn't want to throw it out. But if it's outside the confidence interval, then it's not a plausible value, and then you do want to throw it out. And that is more or less how this works, and now we're going to run through a few examples. I think it's easier to see it with some concrete examples rather than just these statements here. For this first example, I guess the thing that I wanted to point out right at the beginning is the new part, which is the thing that's in red right now. But to kind of run through the whole thing, what we've got up in that top paragraph is we have that last sentence. That's probably the biggest thing. The recent report states that 46% of U.S. households have an Amazon Prime membership. We are going to need that. That's going to be used when we get to the hypotheses in a minute. And then, let's see, Penelope wants to know if this proportion is different for her large hometown. She selects a random sample. There we go. We're going to need that when we get to the conditions. Of 185 households from her hometown, 102 have an Amazon Prime membership. So is there convincing evidence that the 5%, typical alpha, right? 5%, that's alpha being 0.05, 5% significance level that the proportion of households in this town differs from the claim in the report. Okay, so the first thing is we are going to do this with a confidence interval, so you got to get the confidence level and alpha to match up. So if alpha is 5%, then you want the confidence level to be 95%, since 5 plus 95 would add up to 100. Then I think we can write out the conditions for inference pretty quickly. So we've got the random sample. We're looking for evidence that the proportion differs. So there's the two-sided alternative. We said that has to be how this works if you're going to do it with a confidence interval. So we've got that. The one thing that's going to be a little bit different is to check to make sure we have a large enough n, because you actually have an option that time. Since we have the random sample, that'll take care of the randomization. And then setting up the hypotheses, the value from the report was the 0.46. So we're looking for evidence of a different proportion. So we're looking for evidence that for that town, p is not equal to 0.46. So that's going to be our alternative, and then the null would just be the p equals 0.46. The part that's a little bit different this time is the check to make sure you have a large enough n, because you could view this as, well, we're doing a hypothesis test ultimately, so we should do it like the way we do it with a hypothesis test and use p0, so use the 0.46, which is what I have happening over here on the left side. Or you could say, the thing we're actually computing is a confidence interval, so we should do it that way and use p hat instead of p0, and that's this one over here on the right. So there is an option here. They both end up working. And really at this point, I guess it would be one or the other, right? You wouldn't really have to do both. You would just do one of them and make sure that that was all right. So I wrote both of them in there just to kind of illustrate that they both work. But, you know, out in the wild, you would just do this once, not both times. We do need to know p hat, so we'll have to compute it, but we have the numbers and the wording. So out of the 185 households in the sample, 102 had Amazon Prime. So 102 over 185 ends up being 551. And then because we know we're using 95% confidence to match up with the alpha of 0.05 or 5%, then that means that the critical value is going to be 1.96, since this is a test with a proportion, so we can use a standard normal distribution. So we're just going to get 1.96 here. We don't have to look anything up this time. We have everything that we need to sub into the formula to compute the confidence interval. Since we have p hat, we have z, we have n, that's 185. So if you sub everything in, then have the calculator simplify the margin of error, and you'll end up eventually with these endpoints. So I rounded to 4 places on the margin of error since my p hat was going to 3, and you end up with the interval from 47.93 to 62.27. The new part in D is the beginning. How do you handle making a decision about the null? And basically the idea is if the null value is inside the confidence interval, then that's a plausible value for the parameter, so you don't throw it out. But if the null value is outside the interval, then it's not a plausible value, so you do throw it out, so you do reject the null, and that's what's happening here. 0.46 is smaller than the lower endpoint of that interval. It's smaller than 0.4793. So it's outside the interval, which means that it's not going to be a plausible value for p, and if it's not a plausible value, you should reject it. And then the conclusion, the conclusion basically just works the same way that it did before, right? If you're rejecting the null, you have sufficient evidence to conclude what's in the alternative, which here is that the proportion of households with Amazon Prime subscriptions in Penelope's hometown is different than the value in the report, which was 0.46. We have another example. This one is for a mean instead of a proportion, but ultimately that won't change too much. It's still going to be that we're going to compute the confidence interval, and then we're going to have a null value to check and see if it's inside the confidence interval. It's still going to work like that. So what we've got is that the census reported takes workers in a large metro area an average of 28 minutes to get home from work. And then we have a random sample of 65 workers in that area, showed an average time to get home from work of 31 minutes, standard deviation of 6. So there's X bar and S, right? X bar is 31, S is 6, N is 65. The 28 will be the value that we have in our hypotheses. And then we want to construct a 90% confidence interval, and the critical value is sitting right there. There's the INVT. So we don't have to go get it. We can just go ahead and use that 1.669. We have everything that we need to sub into the confidence interval formula in order to compute it, since we have the 1.669 for the critical value. So if we sub in 31 for X bar, 6 for S, 65 for N, and there's the critical value, what you'll get is 1.242 roughly for the margin of error, and then you get this confidence interval here. And then from there, we can make a decision pretty quickly about the null hypothesis. Part B is setting the hypotheses up, and we know it's supposed to be two-sided if we're going to use the confidence interval, but it does also say it toward the end of the wording. We're looking for evidence that the average amount of time to get home in that metro area is something other than 28 minutes. So something other could be higher, could be lower. That is definitely a two-sided alternative. So we end up with mu not equal to 28 for the alternative hypothesis, so mu equals 28 for the null. Part C, the first thing is matching up alpha with the confidence level. That's a 90% confidence interval up there, and we want alpha to match up. So 1 minus 0.90 is 0.10, and that's what we're going to want, right? That way the 0.90 plus 0.10 equals 1. We've got alpha and the confidence level matched up. Then from there, we can make a decision. So is 28 inside the confidence interval? If I look up here at the confidence interval, no, it's not. It's too small since the lower endpoint is 29.758. So 28 comes in below that. That's outside the interval. So if 28 is outside the interval, it's not a plausible value for mu, which means that we should reject the null here again, just like in the last example. For the third example, it does say we have a sample of size 20, so I suppose this is one where we're kind of assuming that we have a nearly normal population, since we have a smaller sample size and we don't have the normal probability plot and box plot here. But we have a 95% confidence interval, and then we're looking for evidence that the mean purchase amount is different than $40 at the 5% significance level. Okay, so there's the alpha, the 5%. So that and the confidence level are matched up. 95 plus 5 is 100%, so we're good to go there. And 40 is inside the interval. So is there evidence that the mean purchase amount is different than 40? No, there is not, because 40 is inside the interval this time. Here's everything for example 3 all written up. So we know it has to be a two-sided alternative, but it is there in the wording. The is different from 40. That's the key. That's the red flag there. And the reasoning for the no up here is that this time 40 is inside the interval. It's between 35.586 and 54.934. So if it's inside the interval, then that means that 40 is a plausible value for mu. And if it's a plausible value, you don't want to throw it out. So that's why the null should not be rejected in this case. So just to have one where the opposite happens, since the first two examples both had rejecting the null, this one you don't reject the null because 40 is inside the interval.